Okay, I happen to be a member of the scientific committee, so as a part of the general introduction, let me say that we are grateful to Microsoft Research and the Pacific Institute for Mathematical Sciences for financial support. Well, I guess the only thing that remains for me to do is to introduce the first speaker, Allan Sly, who is a postdoc at Microsoft Research, and as you will see, who will speak on the Ising model. Please.
Thanks, Chris, and thanks to the organizers for giving me the opportunity to speak this morning. So I'm going to be talking about joint work with Eyal Lubetzky, my colleague from Microsoft, about the two-dimensional Ising model. So the Ising model is a model that comes from statistical physics. It's a model of magnetic systems, kind of the magnetic particles in something like iron. And it's one of the most studied models in statistical physics, and there are literally thousands of papers about it. So you can imagine a bunch of particles, each which will all either be plus or minus, and their positions are given by some graph structure. So graph G, for today's talk, you can always think of this as some subset of the d-dimensional lattice. And so it's a probability distribution over configurations, where a configuration is just an assignment of either pluses or minuses to each of the vertices. And these pluses or minuses I'll call spins. And so the probability distribution weights configurations according to how many pluses are next to pluses and minuses are next to minuses, sort of favoring the configurations that have more like spins in neighboring vertices, according to this Hamiltonian type formula. And so and the strength of those interactions is governed by the parameter beta, which I'll call the inverse temperature. And so when beta is, say, 0, this is just the uniform distribution and all the spins are independent. And when beta is large, there'll be a tendency for most of the spins to be next to, most of the vertices to have the same spins as their neighbors. Okay, so there's been a lot of work on this, on the Ising model going back, well, since Ising started working on it in the 1920s. And for the two-dimensional model, since the work of Onsager in the early 1940s, it's been known, well, established sort of the exact location of the phase transition of the model. So when beta is small, in the high temperature phase, sort of all the spins, the pluses and minuses, are sort of the correlations between them decay very quickly, sort of exponentially in the distance. And so there's no structure. It kind of looks like random noise. Whereas at low temperatures, you have a lot of structure, mainly either, and you mainly have pluses next to pluses and minuses next to minuses. And the reason why you have plus on the top and minus on the bottom is because of the boundary conditions imposed here. And then the point at which you have a transition between these two regimes is at the critical temperature, which is at a beta which is exactly known. Okay, and some of the most interesting mathematics happens exactly at the critical temperature, and I'll talk more about that later in the talk. So this talk will be about sort of the Glauber dynamics, which you can think of as a dynamical version for the Ising model. So it's a Markov chain used for sampling from the distribution, and so which you can think of as kind of the spins randomly evolving over time. So each vertex gets a rate 1 Poisson clock, and when the clock rings for that vertex, you look at the neighboring vertices and work out the conditional distribution at that vertex given the neighbors. And this will just be a function of how many pluses and how many minuses occur amongst the neighbors, and the interaction strength beta. And so then you just resample the vertex according to that distribution. And so this is just one update of the dynamics. And the distribution is stationary and ergodic and reversible, or the Markov chain is ergodic and reversible with respect to the stationary distribution. So eventually, if you run it enough time, it will converge to the stationary measure mu. And so the main question for this talk is, when you have a large system, so the number of vertices is large, how long does it take for this Markov chain to reach sort of statistical equilibrium? So what's the mixing time for it? So there are a couple of different ways you can measure the rate of convergence of the Markov chain. One will be the spectral gap, and this will be the main one I'm going to be talking about for this talk. But you can I'll also talk a bit about the mixing time, in terms of total variation distance. So this is essentially how long it takes for the Markov chain to be close to its stationary distribution from a worst case starting point, say within epsilon in the total variation distance. And the total variation distance is just like the L1 distance between the measures. Okay, and so the question is, for different values of beta, the inverse temperature, how do these parameters vary as the size of the system grows? Okay, so there's been a lot of work on this topic, and there's kind of a general picture for different values of beta. So when beta is large, there's the strengths of the interactions are strong. There's a bottleneck in the for the Markov chain, and it takes exponentially long to mix. So if we fix sort of our graph being a box in the d-dimensional lattice of side length n, then with say either periodic or free boundary conditions, then the mixing time will tend to grow like exponentially in n to the d minus 1. On the other hand, it's expected that at the critical temperature, it should be just polynomial in the size of the system. And then at high temperatures, the spectral gap should be of constant order, so not growing with this, well, not growing beyond a certain point with the size of the system. And the mixing time should be of order log n. And it should also have the so-called cutoff phenomena, which essentially says that if you look at the distance of the Markov chain from stationarity, it in the total variation distance, say, it goes from close to 1 to close to 0 over a very short time period. So this is kind of, so some of this picture is known for some models like the Ising model or parts of it on different graphs. And so I'm going to be talking in particular about the two-dimensional lattice. So I'll tell you, so this is what's kind of expected by physicists and is sort of in line with what rigorous results have been proved so far. Okay, and for the Ising model, a lot is known, and so in the particularly by work in the late 80s and early 90s by Diffusion and Schlossman, Eisenman, Struck, Zegarlinsky, and culminating in work by Martinelli and his co-authors. Both the high and the low temperature regimes are quite well understood. So in particular, at high temperatures, when beta is small and the interactions are weak, the spectral gap is known to be uniformly bounded in the size of the system. and the mixing time is known to be order log n for any beta less than the critical value beta c when you're in 2 dimensions. In higher dimensions, this is only known for sufficiently small beta. And Yuval asked the question, do the dynamics obey the cutoff phenomena? And recently with Eyal, we established this and showed that the mixing time occurs at the inverse spectral gap times log n up to little order factors. Okay, and at low temperatures, sort of work of Martinelli and others confirmed sort of pretty much everything you could ask about the mixing time and the inverse spectral gap, that they're exponential in n, and even the constant in the exponential is known explicitly. So the remaining question then is what happens at the critical temperature beta c? And does this obey the sort of polynomial growth that was predicted? Okay. So first of all, it's known, it's known that it grows at least as fast as a polynomial, and this comes from sort of results on correlation decay, which go back to Onsager in the 40s, and you can also work of Holly in the 90s. So it's at least polynomial, and numerical estimates by physicists seem to confirm the polynomial picture and show that the inverse spectral gap seems to grow at something like n to the 2.17. So, and this seems to be universal in the sense that it doesn't depend on the square lattice. It also seems to be the same exponent for, say, the two-dimensional hexagonal lattices or triangular lattices as well. And yeah, but this 2.17, this isn't a prediction from some sort of non-rigorous or techniques or heuristics. This is just what comes up in the numerics, and there's no actual conjecture about what the critical dynamical exponent should be for this. And in terms of rigorous work, sort of before the work that I'll tell you about in a couple of slides, there were no sub-exponential bounds for the mixing time. So it was an open question as to whether or not it was actually polynomial, and it could be anything up to exponential. This was the question has been answered on the complete graph and the regular tree, and even in these cases, it was like a very challenging result. Okay. So the first time I gave this talk, someone asked the question. It's like, you know what happens in high temperatures and low temperatures? That's like leaves only one particular value of beta. Why do you care so much about this? And it's not just a matter of like completeness and trying to get it for every value. Some of the most interesting mathematics occurs when beta equals beta c. And in particular, it's part of the sort of revolution of the last decade that's sort of been sparked by the advent of SLE. And so recently, or in the last few years, Smirnov described the full scaling limit of the critical Ising model in terms of, if you look at the boundaries between the plus clusters and the minus clusters, saying that these converge to the conformal loop ensemble, which is like a collection of SLE type curves. And for this and other work, he recently won the Fields Medal. And this convergence to SLE, we don't use directly in our proof, but it motivated some of the ideas of it. But we do use Russo-Seymour-Welsh type estimates, which I'll explain later on, which were part of this program of convergence to SLE. Okay. Okay, so the main result is that, yes, indeed, this inverse spectral gap is bounded by some polynomial in N. And this holds for arbitrary boundary conditions. And saying arbitrary boundary conditions here is not just sort of trying to be as general as possible. It's really important for the proof that we prove it not just for one particular boundary condition, but for all of them, because it's the proof is in a sense inductive. The inverse spectral gap grows as a polynomial, and fairly standard estimates show that this also extends to the mixing time in total variation distance, and that's also polynomial. But we don't actually know what the constant C here is, just that there is some fixed constant. Okay. This also gives a polynomial upper bound for the sort of coupling from the past sort of approach to sampling to perfect simulation for the Ising model at the critical temperature. And this was one of the examples in David's with Jim Prop's original paper on coupling from the past and perfect simulation. So we can say that the expected running time is actually polynomial. And we also give an improved lower bound on the mixing time of n to the 7/4. And so this doesn't match the sort of the numerical experiments, but 7/4 is maybe not so far from 2.17. But we don't know how to sort of improve this even heuristically. Okay. So the main techniques are a sort of multi-scale approach, and so you can say, what does it mean to have have the inverse gap growing at a polynomial rate? It means, say you double the size of the box, it means that the inverse gap should increase by, at most, a constant multiplicative factor. So you have to remember where breakfast and the food is. And if you want to know the wireless code, you should probably write this down. So we know, let's say we know that if you look at the bottom 2/3, this mixes well, and the top 2/3, that this also mixes well. How can we take this to sort of a result in terms of the mixing time of this whole box? And that will be the main sort of idea of the proof. And this is essentially what people do in high temperatures, and the point is there to take advantage of the fact that at high temperatures you have sort of strong decay of correlation. So the effect of vertices here is going on a vertex here is very weak if the distance is large. And you can essentially, because it decays exponentially, you can in a sense just add up the effect for each particular vertex. But this approach just doesn't work at the critical temperature, because rather than having exponential decay of correlations, you have correlations decaying at some slow polynomial rate. And so, in a sense, our proof is about saying not what is the effect of conditioning a single vertex, but what's the effect of conditioning the entire face of a box, and proving some weak spatial mixing results about this, and that will make the proof go through. So I guess this slide, I'm going to just explain it in pictures. So suppose we have a box of, say, roughly equal side length and two boundary conditions, psi and eta. And they agree on three of the sides, but psi is not equal to eta on the bottom boundary. What can we say about the two measures inside this box? Well, it could be that one is all plus on the bottom and the other is all minus. So towards the bottom of the box, the measures will be very different potentially. So you can't hope to say that they're similar everywhere inside the box. But what if I just want to say that if this is distance r here, above some level rho times r, what if I'm only interested in the measure above here? And so just to make it even simpler, just the measure in the top half of the box. How much does changing the boundary condition on the bottom affect the measure here? And our result is that if you look at the projection of the Ising model on the top half of the box for the two different boundary conditions, then the total variation distance is sort of less than or equal to some function of rho here, and it's in particular strictly less than 1. So another way of formulating this is you can say, suppose we take these two measures, we can couple them so that on the top half of the box they agree with some probability bounded away from 0. And so this statement is just something purely about the static Ising model. There's no Glauber dynamics at all in here. But now, given this statement, I'll tell you how we do the inductive step to show to compare the spectral gaps on different scales. And this is done using the block dynamics, which is sort of the standard kind of multi-scale approach to understanding spectral gaps for the Ising model and under other spin systems. And so the idea is, so let's say lambda is the rectangle that we want to know the spectral gap for or to bound it on. And so break lambda up into some possibly overlapping sets, BI. Then you can bound the inverse spectral gap on lambda by the inverse spectral gaps of on the BI, on the sub-blocks, but also taking a maximum over all boundary conditions on the blocks. And this is why we need our proof to work for all boundary conditions so that this induction will work. Okay, and then there are correction terms as well. The first one is just the how many times vertices appear in different blocks. And in our construction, you can just take this as being a 2, because there'll only be 2 blocks. And the other one is the inverse spectral gap of what's called the block dynamics. And this is a generalization of the Glauber dynamics, where rather than taking a vertex and updating it according to its stationary distribution, you take a whole block, delete all the spins in here, and update it according to its conditional distribution given the configuration on the complement of the block. And this is again reversible with respect to the stationary distribution, and it will be simpler to analyze. So in particular, we'll take just about the simplest decomposition into blocks that you could ask for. So oh, that's not very good.
When the temperature is critical.
Yes, so this is all about, I mean, this result holds for any temperature, but the analysis I'll tell you now will be relying on the fact that it's at the critical temperature, because it will rely on this spatial mixing result, which is for the critical temperature, which is, so I guess I should have said this is false if you're at low temperatures. And so in particular, that's why you won't get polynomial mixing at low temperatures. Okay, so we have our box and split it up into 2 blocks. The bottom 2/3 of the block and the top 2/3. And our dynamics will go, pick one of these blocks, delete all the spins in it, and update the rest according to the conditional distribution given the rest of the block. So, and what I want to do is show that this has a uniformly bounded inverse spectral gap. And I can do that by showing that it has a uniformly bounded mixing time for any external boundary condition. And I'll do that by showing that given any starting configuration, the probability of coupling within 2 steps is uniformly bounded away from 0. So, so let's say your first step is you update the top block. And so now when updating that, you delete all the spins in the top 2/3 and then look at the boundary condition you have. 3 of them are given by the external boundary condition in the problem, but the bottom one comes from the spins in the complement of the block. And so these could be different in the 2 copies of the chain. But the spatial mixing result says that with some probability that's uniformly bounded away from 0, we can couple them in the top half of the block. Yeah, the top half of the block, and so the top third of the whole thing. And now, say we update the bottom block, then if we've coupled the top half, then they have the same boundary condition in both copies of the chain here. Coming from the top boundary, and the other 3 boundaries are just the same because they're fixed external boundary conditions. So given that we couple the top third, then we can, in the next step, couple the rest as well. So this gives a positive probability of coupling it in just 2 steps. And this, and so in particular, the mixing time is uniformly bounded, and the inverse spectral gap is also uniformly bounded. Okay, so then Well, if you plug this into the formula, so we can take the block dynamics to be have an inverse gap which is uniformly bounded. This n will just be 2. So the inverse spectral gap on the larger block is bounded by a constant times the inverse spectral gap on these sub-blocks. So we can now just do induction, and each time the volume decreases by 2/3, and there's a multiplicative factor of some constant in the inverse spectral gaps. So you do this sort of order log n number of times, and you get some constant to the power of, I guess, 2 log base 3 on 2n, which will just be n to some constant. So this gives the polynomial upper bound on the inverse spectral gap. So the key thing is proving the right spatial mixing result, and that we can indeed say that when we have 2 boundary conditions, we can couple the top half of the block with the probability bounded away from 0. So it would be easier to say how to do this first, rather than for general boundary conditions. I want to say how you do this for 2 specific boundary conditions, because in some sense this was the motivating idea. So suppose on the one hand we just have the all plus boundary, and on the other hand we have plus on 3 sides but minus on the bottom. Okay.
This B plus this B. Well, this is this B, yes?
This is, yeah, so the spins giving the boundary condition will be, yeah, plus here and minus here. Okay, so now you can ask, well, I want to try and couple these distributions so that they agree in the top half. Let's reveal the kind of cluster of minuses on the bottom, which will be which will give some random curve, with minuses on one side and pluses on the other. Okay, and above this curve, you now have plus boundary conditions on all of this space, and so by monotonicity, I can couple these two so that above this random curve, okay, I can put pluses along here as well, and above this random curve, I can couple them so that they're equal, because they just both have all plus conditions everywhere. So the question then is, in terms of whether or not the top half is the same, is does this random curve exceed the sort of the halfway point? And the point now is that Smirnov's kind of results in theory say that this curve should converge to some SLE type curve, well, to an SLE curve. And in particular, well, I'm not going to tell you all the properties of that, but one thing will be that with positive probability, it will stay in the bottom half of the curve, or in the bottom half. So in the scaling limit, the probability of this curve staying in the bottom half will be strictly bounded away from 1. And probability of it staying in the chance of it, yeah, okay. Yeah. Okay, yeah. So the chance that it crosses the curve will be less than 1. Okay, so for these two particular boundary conditions, we can couple the top half with some probability strictly greater than 0, independent of the size of the system. But our inductive proof really needs the result to hold for every boundary condition. And there isn't sort of the theory of the, well, we're also using the monotonicity of these particular boundary conditions, but also there isn't really a theory of what the scaling limits should look like for completely arbitrary boundary conditions. And so instead, to deal with this, we pass to the FK Ising model. So there's okay. So in the FK model, or the random cluster model, is like a, just briefly, like a kind of like a dependent model of percolation. So so you do independent percolation, but then reweight the probability according to the number of clusters you see. And in the Ising model case, it's just according to 2 to the power of the number of clusters. And then the Edwards-Sokal coupling gives a way of relating the Ising model to the FK model. But again, this arbitrary boundary condition that we have is problematic, because conditioning on a particular boundary condition in the Ising model is like conditioning on certain wirings on the boundary, but also on the event that there's no crossing on the FK model from a plus vertex to a minus vertex. And this could happen with, and the chance of this event could be exponentially small for particular boundary conditions. Okay. Like in particular, if your boundary conditions were plus minus all around. But this is a decreasing event, so we can use monotonicity in the FKG inequality, and you can translate the problem into asking, if you look at the corresponding FK model, does the cluster connected to the bottom exceed, say, the halfway point? And this is, and for this we can use the new Russo-Seymour-Welsh estimates developed by Dumnil, Copan, Hongler, and Nolan, and which show that this probability is strictly, or the probability of it exceeding this line is strictly bounded away from 1. Okay, and yeah, and so what we can do is, outside of this component that's connected to the bottom boundary, we can couple everything else and then transfer it to the Ising model, and by the Edwards-Sokal coupling, and couple everything there as well. Okay, so a couple of sort of open questions would be, and these are probably not so easy. Can you calculate the precise sort of universal critical dynamical exponent? We don't even really have a guess for what the correct answer there should be. And also, what can you say in higher dimensions, like, and in particular in dimension 3? Okay, thank you.
Okay, go ahead.
Could you describe again how you coupled these paths at the bottom there?
Okay, yeah. So first of all, you sort of reveal the sort of minus component, and just by looking at one vertex at a time, is this minus or plus, and do that until you can't go any further.
Right.
And then sort of by a monotonicity argument, you can say that, well, along this curve, because this is even more plus, it should be at least as plus, which is all plus, and then in what's remaining, you have all plus boundary conditions on both, and so then it's just yeah.
Right. So that curve there could have some flux underneath it as well.
Yeah, exactly.
Right.
So you sort of already assume that you have the monotone coupling right from the start.
Go ahead. Please.
You mentioned that the numerical experimentation suggested that there should be some kind of universal exponent around 2.17.
Yeah.
Do you have intuition for why that shouldn't depend on the type of graph?
I don't have intuition as to yeah, so no. And I think physicists probably do, and I'm not really sure. Yeah, no, but for a two-dimensional system, if you compare the square lattice and the hexagonal lattice, well, why should they be the same? Yeah, I'm not sure.
Okay, I have a quick question concerning the method of simulating the process. Basically, you're asking a question about convergence to the stationary distribution.
Yeah.
If I understand correctly, the whole procedure would be done at a critical temperature, right? I mean, the simulations. But the estimate also for the mixing time assumes that you can start from any initial configuration, right?
Yeah.
So my point is this: would it make sense to start your simulations at a high temperature, where you have exponential convergence to something, so you get immediately from some extreme or unusual initial configuration to something that looks maybe more standard or normal, and then switch the temperature?
So this is I think goes by the name of simulated annealing, and varying the temperature as you go. And in some models, this does improve the mixing time. And I think definitely you can show that, say, in the if you looked at the complete graph for the Ising model, you could prove that this sort of gives you a faster way of bounding the mixing time at low temperatures, because there's a bottleneck between mainly plus configurations and mainly minus configurations, and if you do it at high temperatures, then it kind of lets the Markov chain choose which one to take. On the other hand, there are other models, like the Potts models, for which it's been proved that this kind of technique doesn't work. So it depends on the model and the graph.
Are your results just for the square lattice, or can you handle any lattice?
Okay. Do the Russo-Seymour-Welsh estimates apply in those ones as well? So, as long as we know these Russo-Seymour-Welsh type estimates, then everything else goes through. And so it depends on that, and I'm not exactly sure.
I mean, if they don't, then not really Russo-Seymour-Welsh. And if they're anything like this functional calculation, then it's robust.
Yeah. I have to get back to you on that.
Okay, I mean, the
Yeah.
follow-up question is, so your results don't use the fact that I mean, in this case, you know explicitly what the beta C is, but you don't need to use that fact. Is that right?
Yeah, yeah. The result depends on crossing probabilities in the.
I think they should because I mean there's only 3 holes everywhere. Like surprisingly for FK Ising and for Ising, they know for any lattice all these conformal theory and for calculation they don't. But yeah,
Right.
I think it works.
Yeah, yeah. So for some of the results, the SLA results, it does hold in general. I'm not exactly sure whether or not they like wrote it down for output, the ones we need in particular. Yeah, but really the important thing is crossing probabilities.
So I mean, your proof is certainly robust to the lattice.
Yes.
Yes.
Okay, let's name the speaker again. The next.
So our next speaker is Ed Waymire, who needs no introduction to people who've been to the seminar frequently. And anyway, here he is.
Thanks, Martin.
So thank you, Martin, and thank you. I have to also thank our local organizers from Oregon who drew my hat out this time to be a speaker from Oregon. And also, not only maybe I don't need an introduction for people who've been here before, but this is also a topic. The last time I spoke here, I think it was the same kind of topic. And there'll be different material, new results, but similar topic. And it's joint work with colleagues at, this is a graduate student, Thilanka Appuhamillage, who's here today, and Vrushali Bokil, Enrique Thomann, and Brian Wood. We're all in math except for Brian, who's in environmental engineering and so forth. And this is work that was supported by one of these math geoscience grants from NSF. I should mention that too, I suppose. And I'm going to start by just sort of describing 3 different examples. This first example, this right here is Brian's lab, and it's a little bit. This is the actual apparatus. What it is it's a column that has two glass beads packed in it. One is the coarse-grained glass beads, and the other is very fine glass. And so on one half, the top half, say, is the coarse grain, and the bottom half is the fine-grained sand, and it's saturated with water. And then, I always envisioned these things until I saw his lab. I always thought they would be horizontal, but his is vertical. But basically, you put dye in on one end, and then the dye runs through, and you measure how long it takes to come out the other end. And so basically what you have as a model of this sort is a fixed law, a flux law. Basically it's a standard like Fourier law or flux law. But the diffusion coefficient is different in the coarse and fine grain. So you have an interface there where there's an abrupt change in the diffusion coefficient. And then usually there's also a flow through a constant rate through the system. These are results of an experiment that were performed at the Lawrence Livermore Berkeley lab of a very similar nature in 2009. And in fact, what I just showed you was Brian's confirmation of these results in the lab at OSU. So what they are basically, they're called breakthrough curves. And they measure how long it takes to go from one end to the other. But they do it in 2 different frameworks. One is that you inject on the coarse grain end, and you retrieve it on the fine grain end, or you can inject on the fine grain end and retrieve it at the coarse grain end. A completely symmetrical situation, However, what these curves are showing, and now the probability problem that you get out of this is that if you have a diffusion coefficient d minus here and a diffusion coefficient d plus here, and the interface is here, and you inject at -1, and then you see how long does it take to come through out here, versus if you inject here and see how long it takes to come through here, with the velocities completely reversed, which is more likely to be removed first? That becomes sort of the question. And what the experiments are showing is an asymmetry in that breakthrough curve. So I'll come back to that, but that's sort of a motivating question involving a problem with an interface. The second example looks quite different, and it looks like a geophysics or oceanography type problem. However, it is that, but it is really, the point of emphasis is more from ecology. And the reason that it's an ecology problem is that if you look at this string of lights here, this is off the coast of Argentina. This string of lights here is a string of fishing vessels that have been there routinely forever, as I understand. And what's going on is that there's a break in the shoreline where the slope off here is fairly flat and shallow, and then there's a steep break. And at that break is exactly where those fishing boats are lined up, because there's an upwelling that's occurring there, and it's bringing all this nutrient-rich water from cold water from below and bringing it up. So it's sort of a food service mechanism for these fish, and it's a very, very important. Upwelling occurs, I'm told, in like 1% of the ocean. And however, upwelling is responsible for like over 50% of fisheries. That's the kind of thing that you can read about these things. So upwelling events do have a big impact on fishing and fish food as a resource. And what's characteristic of this, or somewhat unique about this particular one, is that it's due to this break in the slope. And normally these upwellings are caused by winds. This is a model. This is just to show, I don't want to go through any of the details, a derivation of a model which describes the free surface where you have a break in the slope down here that represents sort of the coastline of Argentina. And when you derive for the free surface, when you derive using just geostrophic balance physics equations, you get an equation which looks like this. And this term here, because it's in the southern hemisphere, is negative. So if you put that over on the other side, you'll have a minus times that. And this is going to be, again, a constant, roughly. It's going to be a constant here and a constant there to indicate a sharp break. And so, again, you have a diffusion equation for the free surface with well, that should be a minus, sorry. Yeah, you have two different diffusion coefficients at an interface, the interface being caused by that break. So that's my example number 2 of, again, a diffusion equation of where there's an interface. And the third example is an example that it's literally from my backyard in some sense. I'll tell you why. The Fender's blue butterfly is a butterfly that's on the endangered species list. And in fact, it's in the Willamette Valley of Oregon where they live. And what they do is they live in these, what they like are these patches of lupin. Here's what one lupin looks like. But they like these big patches of lupin. And the ecologists, because they're on endangered species, there's a lot of literature, statistical literature about them. And I just quoted here one just to give a sample of the kind of questions. This is from an ecology journal. Given past research on Fender's blue and the potential to investigate response to patch boundaries in this system, we asked 2 central questions. First, how do organisms respond to habitat edges? And what are the implications of this behavior for their residence times? So I indicate this just as another example. What's going on is there's a distribution of these lupin patches throughout the region. And when butterflies are in these lupin patches, they're very happy and they tend to kind of just wander around and not move too quickly. But when they get outside of their patch, you know, they're kind of worried and they kind of fly around all over the place. So they have a different kind of dispersivity rate when they're outside a patch versus when they're in a patch. So these are sort of just 3 examples to show the somewhat natural consideration of interface problems. What's different about the 3 examples, however, is what happens at the interface. In the first example, because of just conservation of mass, the natural interface condition is continuity of flux across the interface. Because this is consistent with what's observed, it's consistent with this Fickian sort of model of diffusion, and so forth. However, for the free surface in the oceanography example, it's the continuity of the derivative that is imposed by the physical considerations. In the case of the butterflies and so forth, this is sort of a new example to us that we're kind of getting interested in, but I'm not quite sure how to address what the interface condition actually is, and that'll require looking at more data and so forth. But in general, the interface conditions are conditions on at the interface of this form, and you know, you can, by dividing this by d plus d minus, you can think of a lambda there. So and here it's lambda is equal to 1/2. So you have different conditions of that form. So this is probability. So let's kind of at least go back to a little bit of probability. And if you think about, although one can argue whether Feller's classification of diffusions is certainly motivated by probability, but it's more or less an analytic resolution of that question. But I just kind of reminding you here that Feller, according to Feller's theory, you know, given these coefficients, just measurable coefficients, there's a diffusion corresponding to that because it'll determine a speed measure and a scale function. And so you can ask yourself, or you can try to work out, what would be the interface condition in the case of Feller's diffusion that you would get from this. We can talk about that later. Similarly, one could go to Struck-Veredan, and you can pose a martingale problem. So Struck-Veredan, given those coefficients, and for the given generator, would say, you know, you look for a martingale for all f in C infinity for those given coefficients. And if you apply that, then what happens as a consequence of the Struck-Veredan formulation, you get a solution, but because of the test functions are all C for the domain are all C infinity functions, you get an interface condition which is the continuity of the derivatives. So then you can ask, you know, well, what do you do about other interfaces from this point of view? And one approach to answering that question is just to say, well, you know, you can, by transforming space, you can make, if you have a given interface condition, so I denote that by if belonging to I lambda, that's just notation to mean that you have this interface condition, well, then you can transform space so that the composition is with 1/2, so it's continuous derivatives, and then you can adjust time and then solve for the process as a Struck-Veredan problem using this, and then sort of go backwards and get a solution that for the given problem. But again, this is still kind of analytic machinery. It's kind of an analytic approach to this problem. I mentioned here Alknine, who also has worked in this area, and he, by his approach, has been one of them was to look at. I wrote that operator in divergence form, and then you look at it as a diffusion with generalized coefficients, and I believe that he has a very similar resolution of this, what I call this remedy to the martingale problem anyway. So I just mention it here. But I'm going to put up here, this is sort of the students from OSU know this is one of my favorite quotes. And it's a quote from that, you know, I don't know that how many probabilists see this, but it's from Jean-Baptiste Perrin's little notebook called Atoms, which is just a wonderful little thin book. which is the notebook that he wrote while he was doing experiments to determine Avogadro's constant after Einstein had shown that the diffusion coefficient could be viewed either statistically or physically, and so they set about to do all these experiments. And I just want to for me, I think he got a Nobel Prize for determining Avogadro's constant. Well, that's an important thing, so it's worthwhile. But this, to me, really shows his genius. And he says at the time, trajectories are confused and complicated so often rapidly that it's impossible to follow them. The trajectory actually measured is very much simpler and shorter than the real one. Similarly, the apparent mean speed of grain during a given time varies in the wildest way in magnitude and direction and does not tend to a limit at the time taken for an observation decreases, as may be easily shown by noting this is really primitive camera technology that they had, but it's amazing that they did do these kinds of photography, and they went from 20 a second or every 5 seconds or minutes to 5 seconds to 20ths of a second. And it is impossible to fix a tangent even approximately at any point on a trajectory, and we are thus reminded of the continuous underived functions of the mathematicians. So, I was always kind of, we always get scooped by physicists in terms of what people really know, and so I was just really amazed by this quote. So, but I really put it here because I want to get away from really the analysis problem and ask more the question of, what would Perrin see if he were looking, for example, at this solute under a microscope? And a first step toward the probabilistic solution to that is given by the notion of skew Brownian motion, which I did talk about here once before, and probably is familiar to most everybody here. But basically, you have an interface condition on the functions in the domain of the Laplacian. And they ask the question, well, how do you construct a stochastic process which would have this as its Markov process with this as its generator on this particular domain? And the answer is that you take a reflecting Brownian motion, you start with that, and then you enumerate the excursions, and then you go through and you toss coins, and if you get a tail, you flip it down, otherwise you keep it up. So +1 is head, -1 is tails. And you go through, and so then this gives you a formula in terms of the reflected Brownian motion, ANs being the plus or minus ones, and JNs being the excursion intervals. So you get a nice formula for Brownian motion, and then this was actually in a paper of Ito and McKean, and eventually then appeared in their book as an exercise. Those of you, there's a wonderful presentation by Henry McKean at the Osaka SPA meeting, and he really conveyed this idea that with Ito, all of the analysis about whether he could understand something, I'm paraphrasing quite a bit here, he said it much more eloquently, was really, or whether, what was the particle path doing? He wanted to know what the stochastic process was in order to understand analytic results. This also is in that spirit of trying to understand the solutions to these problems in terms of the stochastic process. So now with Ito and McKean, given the existence of skew Brownian motion, that doesn't really solve the problem of what is the particle process that you're going to get in these various examples, because you have to tell me what alpha is, for one thing. And probably if you can tell me that, then we can scale it by square root d plus when it's on that regime, and square root d minus. The scaling is going to be relatively straightforward, but you have to find out what alpha is. So I want to just consider here that same problem is just very much like the Ito-McKean problem with an interface condition here that's given by lambda, and pose the proper martingale problem. And the proper martingale problem, which would correspond to these conditions, is given here. And then I want to now take advantage of our guest and a very early result of his, I think his PhD thesis, I guess, where Jean-Francois showed the existence of solutions to stochastic differential equation of this form, where this is local time. And you apply Jean-François' theory with a little Ito Tanaka, and ultimately you get a solution to that martingale problem by observing that the process satisfies this stochastic differential equation with this local time term. So all you have to do really then is make this equal to 0, and then you make this equal to 0, and then that tells you what alpha is in terms of lambda and the diffusion coefficients. And so the solution is given here, just doing the algebra. Alpha is given by this combination of diffusion coefficient and interface parameter. If we apply that to the examples, the first two examples are really the only two examples that I have where I know what the interface condition is. In the first one, the lambda was d plus over d plus plus d minus. That's because we wanted to have continuity of flux. So you just put that into this equation up here, and then you find out that the proper alpha star is given by this ratio. For the continuity of the derivative, lambda was 1/2, and you substitute that in, and you get, this is the proper alpha to use for the representation in that problem. There is one of the really nice consequences after Ito and McKean of the introduction of skew Brownian motion was a paper by John Walsh where he was observing, I mean, at the time, the questions, I mean, other than reflecting Brownian motion, were about having continuous semi-martingales with discontinuous local times, and John Walsh pointed that out as a basic property of skew Brownian motion. And one of the questions that we've been trying to deal with, ultimately, we would like to be able to talk about these phenomena in higher dimensions. There are many higher dimensional problems, the butterfly problem being an example, but there are others, where you'd like to go to higher dimensions. And we're trying to find other ways of thinking about how you can arrive at this parameter or these kinds of transmission probabilities, alpha, or transmission. And one of the things that we wondered about was what would happen if we go to example 1. In fact, I think the last time I was talking about this stuff, after the meeting, I was talking to someone and wondering about, sort of out loud about whether there was some physical reason for maybe you could get continuity of local time as a way to also characterize this alpha. And it does turn out that in example 1, that the modified local time is continuous if and only if alpha is equal to alpha star. So this is another characterization of this particular value of alpha is continuity of what we're calling here modified local time. So what is modified local time? Modified local time means that in defining the local time, typically you integrate with respect to quadratic variation of the process. So, for Brownian motion, it doesn't matter because it's dt is dt and is a big measure. But for these processes, it turns out that the usual local time that you're considering is where you integrate with respect to quadratic variation. And of course, for skew Brownian motion, it's also Lebesgue measure. So, but in the case of this so-called physical diffusion for this given constants, if you integrate with respect to Lebesgue measure, then in place of the quadratic variation, then you do get continuity. And I hope I'm making this as clear as I want to make it. The point is that there's a physical process associated with these problems, and that physical process is not skew Brownian motion. It has skew Brownian motion with this alpha and scaled by those coefficients. So it's a very special structure that way. And it's the local time of that process, if you define local time by integrating using Lebesgue measure instead of quadratic variation, that will be continuous. And the reason that's of interest, as I say to us, is that we're just looking for other ways to probabilistically characterize these choices of parameters. And I must say, though, that Brian Wood, who's the engineering guy, the environmental science person in this project, he was really happy when we changed over to that definition of local time for this result, because it had physical units that made sense to him that didn't make sense to him ever when we talk about, if you think about the units of local time, it's not time in the case of when you define integration with respect to quadratic variation. Anyway, so let's come back. I want to now use this to look at this problem that you get. Let's suppose that, so I have the coarse, the fine grained glass on this side and the coarse grain on that side, and I can either inject and retrieve it over here or inject it here and retrieve it over here. And the question is, which one would get out quicker? Do people have intuition about that? I won't take a vote, but speak up if you do. Okay. So the answer is that, according to the experiments, that if you inject at -1, it will arrive faster at 1 than when it's injected here. So find a course is faster than course defined. And I just want to kind of go through a little bit of the exercises to explain that. So what one would first do well, here's the theorem. It's, I guess it's a little bit stronger. There's a constant times that, actually, that is less than. But there's a stochastic ordering of the breakthrough times in going from -y to y versus going from y, where here y is equal to -1. Or y is equal to 1, sorry. Yeah, y is equal to 1. And so there's a stochastic ordering of the first passage times in going from left to right versus right to left. And it really is a strict inequality, and there's actually a constant there. But to prove that, and I don't want to go through, it's too much here on the screen. But the obvious place to start is with skew Brownian motion, right? You just take skew Brownian motion and you take alpha bigger than half, and then you see if there's an ordering here, and there is an ordering here between the first passage times for just skew Brownian motion, and there's this is a factor of 1 minus alpha over alpha in that ordering, so this is less than that. So there is an actual stochastic ordering, and the proof is based on looking back at this. There's a natural coupling that you can write as plus or minus coin tossings all in terms of a single sequence of uniform random variables. So you have this, so it gives you a way of comparing the effects of alpha and drawing the curves and so forth. So there's a way of actually using that representation to make this calculation. So at least for skew Brownian motion, you show, well, there is that kind of stochastic ordering of the passage times. But for the physical diffusion process, it's a little bit different, because there are also, you have to scale that. And the scaling kind of has the opposite effect as alpha. And so it's shown here in the calculations because they're appearing in reciprocals of these scalings. However, nonetheless, you have to believe me, but because I'm not going to go through, I'm not any good at explaining on these slides like this anyway. But I want to give enough here to show that there are competing things going on between the alpha and the diffusion coefficients over in the fast and slow regime. So you basically work with 4 different inequalities, and you end up showing that there is a stochastic ordering of the passage times. So that's consistent with the experiments. This is actually my last slide here, because there's an alternative, and I think this is more or less what I talked about last time when we were here. An alternative to this stochastic ordering, and this is a more of the first passage times, is actually to compute the resident concentration. I mean, to solve the PDE, And one can do that by a change of measure, and it converts the problem into a problem where ultimately what you really want to know are the distributions of a skew Brownian motion position, its local time, and an occupation time of the positive axis. You have to know how much time it's spending on the positive axis. And we were able to derive a nice simple density, which I'm just showing here, for the triple density in the case of these three processes that basically extends. There was, in the case of Brownian motion, this triple density was known by who was it? I can't remember now. A formula had been known in the case of where this alpha is a half. But in that case, you can plot, this is actually just the flux and then rescaled by a cross-sectional area and the velocity. So this is really just the flux. And you can, by a plot of that, you also see these curves which are showing the same kinds of shifts that are showing in the experimental curves. The question of whether or not those are first passage times or these kinds of flux curves, you know, from an experimental point of view is a little bit, I think it can go either way, because it's really neither, because of, you know, experimentally when you measure, are you really measuring, to measure actual first passage is a non-trivial object, as well as measuring this actual flux. So they're both consistent with experiment. And finally, I'll put a problem up that we can add to Yuval's list. In the case of first passage time distributions for skew Brownian motion, recently Thilanka and Dan Sheldon, Dan is a postdoc at OSU, and Thilanka, they were able to compute the first passage time for skew Brownian motion by analyzing excursions of Brownian motion, and that's on the archive. But what's the open problem is that to try to find a formula for skew Brownian motion with drift, and, you know, unlike the case of Brownian motion, where that's an easy problem because you do a Gersonov and so on, in this world of discontinuous coefficients and so forth, you have to contend with local times all over the place, and it makes it not so obvious, at least to us. So I think that's the end of it. Yes, thank you. Excuse me, one more thing. So I usually try to help out with Bernoulli Society these days. And I have in the back forms. One is for the next Stochastic Processes conference, which will be in June in Oaxaca, Mexico. And I put the flyers back there. And also, especially for graduate students, because membership is free in Bernoulli Society. It's subsidized by the Bernoulli Society for graduate students. And so there's membership forms, the membership forms for everyone, but in particular, graduate students have an opportunity to have free membership, and there are benefits for that. Okay. Thank you again.
So, any questions?